Welcome to this lecture on the pathogenesis of Parkinson's disease. Today, we are going to explore exactly what happens inside the brain when this condition develops. We will start with the biological mechanisms, understanding the specific neurons and proteins involved. Then, we will look at the mathematics of how this disease progresses over time. By the end of this session, you will have a comprehensive understanding of both the cellular causes and the clinical timeline of Parkinson's disease. Let us dive right in. Now that we have introduced our topic, let us start by imagining the brain as a complex, beautiful clockwork machine. For the thousands of interlocking gears in this machine to turn smoothly and keep perfect time, they need a very specific type of lubricating oil. In your brain, these gears are the motor control centers that help you walk, reach, and move effortlessly. The oil that keeps them running is a chemical messenger called dopamine. Now, imagine that the tiny factory inside this machine that produces the oil slowly starts shutting down, worker by worker. Without this crucial dopamine, the gears start to grind, stutter, and eventually lock up completely. This is the intuitive foundation of what happens in Parkinson's disease. Moving from our clockwork analogy to the actual biology, let us look at the formal definition of this pathogenesis. Parkinson's disease is a progressive neurodegenerative disorder that primarily affects the motor system of the central nervous system. The core biological mechanism is the selective death of dopaminergic neurons. These specific neurons are located in a midbrain region known as the substantia nigra pars compacta. As these vital neurons die off, there is a severe depletion of dopamine in another region called the striatum. The striatum is a critical part of the basal ganglia circuit, which is entirely responsible for executing your voluntary movements. When the striatum lacks dopamine, the brain simply cannot send the proper signals to the muscles. Understanding where the neurons die leads us to ask why they are dying in the first place. At the cellular level, a major hallmark of Parkinson's disease is the abnormal accumulation of a misfolded protein called alpha-synuclein. Normally, proteins must fold into specific shapes to function correctly. However, when alpha-synuclein misfolds, it becomes sticky and forms toxic clumps inside the surviving dopaminergic neurons. These dense, abnormal structures are known as Lewy bodies. As Lewy bodies gather and grow, they severely disrupt normal cellular functions, effectively choking the neuron from the inside out. This toxic buildup is a primary driver that accelerates the death of these crucial dopamine-producing cells. Now that we know the biological mechanism, we can see why this knowledge is absolutely crucial for real-world medicine. Understanding the exact pathogenesis directly dictates how we treat patients suffering from Parkinson's disease. Because scientists discovered that the core issue was a lack of dopamine due to dying neurons, they were able to develop a medication called levodopa. When a patient takes levodopa, the brain converts it into dopamine, temporarily replacing what is missing and alleviating debilitating symptoms like resting tremors and muscle rigidity. Furthermore, understanding the role of misfolded alpha-synuclein proteins opens the door for future therapies. Instead of just masking symptoms, future drugs might stop the disease progression entirely by clearing out those toxic Lewy bodies. While the biology explains the cause, we need mathematics to understand the timeline. This brings us to the mathematical representation of neurodegeneration. The death of dopaminergic neurons over time can be accurately modeled using an exponential decay function. The formula is n of t equals n0 times e to the power of negative kt. Let us break down these symbols. N of t represents the number of surviving dopaminergic neurons in the substantia nigra at any given time t. N0 is the initial number of healthy neurons present before the disease started. The mathematical constant e is the base of the natural logarithm. The variable k is the decay constant, which tells us the rate at which neurons are dying each year. Finally, t is the time elapsed in years. If the decay constant k increases, neurons die much faster, causing a steeper drop. If a drug could decrease k, neurons would survive longer. Now that we have our exponential decay formula, let us apply it to a real clinical scenario. We are given that a healthy substantia nigra contains approximately 400,000 neurons, and clinical symptoms appear when the count drops to 30%. The decay constant is 0.05 per year. We need to find the time t when symptoms become visible. We set up our equation by substituting n of t with 0.30 times n0. Next, we divide both sides by n0, which beautifully cancels it out. To get the variable t out of the exponent, we take the natural logarithm of both sides. The natural log of 0.30 is approximately negative 1.204. Finally, we divide by negative 0.05. The negative signs cancel out, giving us a final answer of 24.08 years. This means the disease silently destroys neurons for over 2 decades before a patient ever notices a tremor. The calculation we just performed reveals a profound biological truth, which we will now prove formally. We want to establish that the time to symptom onset is completely independent of the absolute starting number of neurons. Let us set up the proof by defining a variable p as the percentage threshold where symptoms appear. Therefore, the number of surviving neurons at onset is p times n0. We substitute this expression into our standard exponential decay equation. Now, look at both sides of the equation. We can divide both sides by the initial neuron count, n0. This mathematical operation cancels out n0 entirely, leaving us with p equals e to the power of negative kt. This crucial step shows that the initial reserve of neurons has already vanished from our equation. Continuing our derivation, we will now solve for the exact time variable. We start with our simplified equation, where the initial neurons have been canceled out. To extract the time variable t from the exponent, we apply the natural logarithm to both sides. The natural log is the inverse function of the exponential base e, so it effectively cancels it out on the right side, leaving us with the natural log of p equals negative k times t. Finally, we divide by negative k to isolate t. Our final result shows that time t equals the negative natural log of p divided by k. We have successfully proven that the timeline to reach the symptom threshold depends entirely on the percentage threshold and the decay rate. Whether a person starts with 400,000 or 500,000 neurons, the timeline remains mathematically identical. Now that we have proven how the neuron count decays, let us look at the direct chemical consequence. Since dopamine production is directly proportional to the surviving neuron count, we can use a modified version of our exponential decay model to track dopamine levels. The formula is d of t equals d0 times e to the power of negative kt. In this version, d of t represents the daily dopamine production at any given time t. The symbol d0 represents the initial healthy baseline dopamine production before the disease began. The exponential term acts as a multiplier that represents the fraction of the original production capacity that still remains active. As the decay constant, or time, increases, this multiplier shrinks, reflecting the severe loss of the chemical messenger that the brain desperately needs for motor control. Let us put this dopamine formula into practice with a concrete example. Suppose a healthy brain produces a baseline of 150 micrograms of dopamine per day. A patient has been experiencing neurodegeneration for 10 years with a decay constant of 0.08 per year. We want to find their current daily dopamine production. We substitute our known values into the equation. D0 is 150, K is 0.08, and T is 10. Multiplying the exponent values gives us negative 0.8. We then calculate the value of e to the power of negative 0.8, which is approximately 0.449. Multiplying this fraction by the initial 150 micrograms gives us a final answer of 67.35 micrograms per day. Physically, this means the patient's brain is only producing about 45% of its normal dopamine, pushing them dangerously close to the symptom threshold. To consolidate all the mathematics and biology we have discussed, let us look at this diagram. You're seeing a graph of neuron decay over time. The vertical axis represents the percentage of surviving dopaminergic neurons, starting at 100%. The horizontal axis represents time in years. Notice the solid black curve sweeping downwards. This is the exponential decay we just calculated. The most critical feature here is the horizontal dashed red line at the 30% mark, which is the symptom threshold. The large green shaded region represents the pre-symptomatic phase. Look at how wide this green area is along the time axis. This visually reinforces what our math proved. The disease operates silently for decades. It is only when the curve crosses into the red shaded region, the symptomatic phase, that the dopamine levels drop low enough to cause visible tremors and rigidity. We have covered a lot of ground today, so let us summarize the most important ideas. First, the pathogenesis of Parkinson's disease is fundamentally rooted in the progressive death of dopamine-producing neurons in the substantia nigra. Second, this cellular death is largely driven by the toxic buildup of misfolded alpha-synuclein proteins, which form Lewy bodies and choke the neurons. Third, because the brain has a massive reserve of these neurons, the disease operates silently for decades. Symptoms only reveal themselves when dopamine levels drop below a critical threshold of about 30%. Finally, by using mathematical exponential decay models, we can accurately predict this hidden timeline and better evaluate future treatments aimed at restoring lost dopamine. You now have a solid foundation in both the biology and mathematics of Parkinson's disease. Thank you for watching.